Hi everybody, hope that you're doing okay today. In the last video that we did in chapter 2, section 2, and we were looking at functions being illustrated by their graphs. And in that section we looked at the vertical line test, and we also identified the domain and the range directly from the graph. Now we're going to move to 2.3. And in 2.3, we're looking at functions in another mode. And the mode that we're looking at it in 2.3 is functions can be identified by their equations. So the emphasis in 2.3 is, first thing, is that functions can be defined by looking at their respective equations. And then the last thing that we're going to be looking at in 2-3 is entitled the algebra of functions, simply kind of meaning two functions can be combined together by either using addition, subtraction, multiplication, or division. And when we get to that part of 2-3, there will be some very specific rules, formats that we'll follow to combine these various functions together. But we're going to turn our attention first to letter A of 2.3. And it is identifying the domain of a function that is being represented by an equation. Now notice in this section right here, it did not include the range. We are only concerned about identifying the domain of the function when it is represented by an equation. Now here is a pretty straightforward rule that we can follow, and we'll describe this a bit. The domain of most functions being represented by an equation will be all real numbers. In other words, every single number that would appear on an x-axis, because those are domains, every single point on an x-axis would represent all real numbers. And like this statement says, most all functions that are represented by equations will have as their domain all real numbers, which when we identify it, we will be using interval notation, and the interval notation for all real numbers is a parenthesis, negative infinity, comma, positive infinity with a closed parenthesis. It must be parentheses because parentheses will indicate that there is no stoppage. It's going to begin somewhere in the negative infinity area, and it's going to end somewhere in the positive infinity, but there really isn't any beginning, and there really isn't any end, and that's why the parentheses are used. If brackets were used, that would signify closure. That would signify that there would be either a definitive beginning or a definitive end. So you want to make sure that you're aware of that interval notation symbol. That's negative infinity, positive infinity. That stands for all real numbers. Now, people, you heard me say a couple of minutes ago that most functions represented by equations would have as their domain all real numbers. But there are two significant exceptions to that rule, and we need to headline them. Exception number one. If your function being represented by an equation, there's the equal sign, if that equation contains a fraction and the denominator of that fraction contains the domain x term, a domain expression. A domain expression would be an expression that would contain the variable x, because x is associated with domain. So if the function defined by an equation contains a fraction, and the denominator of that fraction contains an x term, then number one, the domain of that type of function will not be the entire real numbers. It will be almost all of them, but not all of them, because we studied when we were looking at rational expressions. In rational expressions, we cannot let the value of the denominator of any fraction be zero. Because if the denominator of a given fraction is zero, it would make it undefined. Now, if the denominator contains an expression that includes the domain value of x, it is important to be able to identify the value of x that will cause this denominator to be undefined. And whatever that value is that will cause that denominator to be undefined, that value must be rejected from the domain, from the set of values that would represent the domain. If I can just share this little move right here on this one. While I'm talking about it, let me share. What I'm about to do right here is not new. It is something that has already been discussed in a prior course. We need to find the value of x that will make the overall value of that denominator a zero. Whatever this expression takes to make the value of that denominator a zero, that value of x has to be rejected from the overall domain set. And this was called a restriction at that time. And to identify what x can't be, we take the denominator expression. I'm just going to kind of put it right here. We pull that denominator expression off, and we set it equal to zero. We set it equal to zero because we want to find the value of x that, when substituted into that expression in that denominator, would cause the value of that denominator to be zero. So if we let x minus 1 equal 0 and solve that equation for x, we'd add 1 to both sides, and we would find out that the domain value of x cannot be equal to 1. So that would mean 1 cannot be a part of the domain. Every other real number can, but 1 cannot. Now, when we get to the exercises today that we are literally going to show and identify what the domain is, then I'll show you the interval notation of how this exception is going to be written. All I'm carrying across to you right now is one of the exceptions is if the equation defined contains a fraction where the denominator contains the variable x term, and in that case, we need to identify what that value of x can't be that would ordinarily cause that fraction to become undefined. What it can't be in this illustration, x can't be 1. It can be any other real number, but it can't be 1. And like I said, we will show you the interval notation when we get to an example like this. The second exception is when we are dealing with a square root function. When the x term, when the domain term is a square root radicand. The radicand is the item underneath the radical sign. When that domain letter of x is the radicand of a square root function, the domain, once again, is not the entire set of real numbers. It's most of them, but there will be an exception, and we will point that out right here. Remembering back to this symbol right here, this radical sign, this square root symbol. In order for this radical to be defined for the set of real numbers, the radicand cannot be negative. There is no real number square root if the x, or if the domain, is a negative number. If x is a negative 4, if x is a negative 4, there is no positive square root of negative 4. It can't be 2 because 2 times 2 is 4, and it can't be negative 2 because negative 2 times negative 2 is 4. So for this square root function to be defined, the domain cannot be any real number. The domain cannot be a negative number. The domain has to be 0 or larger. The radicand must be a non-negative real number. Non-negative, not negative. But it can be 0, and it can be any positive number. So this cannot be the entire set of real numbers. When we get to one like this in the exercise that we'll do, we will again show you the interval notation that will identify the domain of it. Now, I'm going to erase some of this area right here because I've got my examples over here that I'm going to do. And you've had a chance to look at this, and you've had a chance to write it down. It has been showing on that video already for a few minutes. So you can always go back and hit the pause button and jot these exceptions down as you need to jot them down. But we're going to turn our attention to this. Directions. We want to simply identify the domain of these functions that are being represented by equations. So we go to number 1. Number 1, I'm going to kind of read it actually in the way that it should be read. I know a lot of people will read on number 1, they'll say f of x is equal to 3x plus 5. But remember, folks, f is defined as the name of the function. X is the domain of the function, and the entire f of x is called the range of the function, or y. Remember from previous videos, f of x is the range, and f of x also means y. So actually, this equation can be thought of as y is equal to 3x plus 5. We're showing it using function notation. Now, we are asked to identify the domain for number 1. There is no work. There is no work because, first of all, there's no fraction whatsoever on the right-hand side, and we're not dealing with square root. We are looking at a function that, by the way, folks, is called a linear function. Because if we were graphing this function, its graph would be a line. And by the way, if I can just insert this, since f of x means the same thing as y equaling 3x plus 5, you should already know when looking at y is equal to 3x plus 5, that equation is written in slope-intercept form. So to this function, this linear function right here is written in slope-intercept form because remember the value of f of x is actually y. So because there's no fractions involved and there's no square root, the domain is the entire set of real numbers, and it is this. And it's done. You see, what we're saying is there is no restriction whatsoever on what you can let x be. You can let x be any real number. You can let x be 0, and you're going to get a unique value for y. You can let x be 1, and you're going to get a unique value for y. You can let x equal -1, 2, -2, 3, -3. You can let x equal any fraction. You can let it be a decimal. And each value of x will lead to one and only one value of the range or y. X is not limited. The domain x can be anything, any real number. Number 2. Likewise, h of x is equal to 3/4 x minus 2. Now true, we are seeing a fraction there on number 2, but there is no domain positioned in the denominator position of that fraction. That domain of x is actually in a numerator. It's not down here by the 4, it's not in the denominator. It's 3/4 x minus 2. And once again, no domain letter in a denominator, no square root function. The entire set of real numbers. No work. Now we come to number 3. F of x is equal to 4x over x minus 2. The light bulb has to go on. You have to take a look at that expression that's on the right-hand side, and you notice not only do we have a fraction, but we happen to have a domain letter of x in the denominator. And when that happens, that signifies that the domain of this equation will not be the entire set of real numbers, because what we're going to have to do is reject any value of x that will make this denominator a 0. That would make this fraction undefined. So, when the fraction occurs, and there's a domain value of x in the denominator, step number 1, pull that denominator off to the side. Just pull that denominator expression off to the side. And set it equal to 0. And then solve that equation. And whatever the solution to that equation is, that is the value that cannot be a part of the domain. X equals 2. That's your restriction. Now, to really show to you that it cannot be included, we'll say, hey, x, you cannot be 2. Hey, domain, you cannot include 2. You cannot be 2. So here's how we'll identify the domain for this particular problem. It can't be 2, but it can be any real number less than 2 or, that's going to be a key conjunction, or the domain can include any real number greater than 2. And here's what it would look like in interval notation, or here is one way. Start with a parenthesis and end with a parenthesis. Put a comma. In this parenthesis unit right here, we're going to identify the part of the domain of where we can take any real number that is less than 2. So we're going to put the greater number on the right, 2. Now notice, with that being a parenthesis, 2's not included. And all of the values that are less than 2 would be negative infinity. That's taking into account all of the real numbers less than positive 2. Then we either write or I'm going to put another symbol above it that some of you folks might be aware of. It is a symbol that means the same thing as or. It's a symbol that's used in sets. And it's a U. It's actually a union symbol. But either one of these can be used. As far as chapter 2 is concerned, they would use or. But if you're familiar with him, you can use him. Now, adding on to this, we're going to have to take all of the real numbers that are greater than 2. So we put another parenthesis, and we'll end with another parenthesis. And now, because we are dealing with all of the values that are going to be greater than 2, then we'll have to begin this portion of the interval notation with the smaller value of 2, comma, and then it will move in a positive infinity direction, and we'll have it. You see, what we just defined right here was primarily this. This is what we did. You see, too, you don't count. You don't count. But you do. You do. And you do. That parenthesis opened up in a positive, and it did here. And this one opened up, moving in the negative, and it did. That would be the interval notation for that function. What does it really say? It can be any real number, but not 2. Okay. Number 4. Just to show you another one. G of x is equal to 1 over x plus 4 plus 3 over x minus 6. Your eyes look over on the right-hand side and they see fractions. When your eyes further look at the denominators, there's a variable expression containing x in this one, and likewise here containing x. X is the domain, so there are going to be restrictions. The domain cannot be the entire set of real numbers. It's going to have some exclusions. So we'll pull each one of them off to the side. X plus 4 and set it equal to 0. And x minus 6 and set it equal to 0. And let's identify our first restriction, our first exclusion of domain. Negative 4, x cannot be equal to negative 4. So that's a number that cannot be a part of the domain. Positive 6, x as well cannot be equal to 6. So maybe just looking at a number line first. Not throwing in a whole lot of numbers, but just putting a number line down. And maybe just sticking a 0 there. And putting the negative 4 right about here. And the positive 6 right about here. It can't be him, and it can't be him. But just think of this as an x-axis. It can't be -4, but it can be any real number less than -4. That's going to be part of the domain. Second part, it can be any real number that is greater than -4 and less than 6. It can be all of these real numbers in between these 2 points, not including those, but in between. Or it can be any real number that is greater than +6. So maybe with that aid, let's go after it. The domain. Let's do this portion of the domain first. We'll begin with a parenthesis. We will end with a parenthesis. The largest value of this interval will be -4, so it's written to the right. And it's moving infinitely negatively. So that's picking up all of those. Or parenthesis, parenthesis. Now we'll take all the real numbers in between those 2 excludable points. The smallest value is -4, and the largest value is +6. With the parentheses there, -4 doesn't count, 6 doesn't count, but all of these do. And then finally, or, and it will be one more parenthesis grouping, starting with the smallest value of that interval, and then moving in a positive infinity, and there it is. That would represent the domain for that function. Now just one more. We'll do a square root 1, so you see. I alluded to it, but now we'll do it. Let's start with this one. F of x is equal to the radical of x. It's square root. Notice the domain value is in the radicand position. Cannot find a positive square root of a negative number. So you see the domain cannot include all real numbers. The domain must be any value that is greater than or equal to 0. You see, x can be 0. It can't be negative, but it can be 0 or greater. So the first thing I want to share is, if you bring down that radicand, the symbol that you now use to identify what your domain is going to be, you let x be greater than or equal to 0. For this one, x can be equal to 0 or greater. Now, to show the interval notation, the domain, you would not begin with a parenthesis, you would begin with a bracket. The smallest value of the domain is 0. He counts. Put 0 in there. The square root of 0 is 0. It's defined. Put a comma and a positive infinity, and he gets a parenthesis, and that would be the domain of that. That is excluding negatives. Now, one more square root function, and then we'll call it on this particular one, and we'll resume back with you in a few minutes. Let's go to this, just so that we see it. Another square root function. we cannot let x be any number that will cause the overall value of that radicand to be a negative number. He cannot be a negative number. So to identify the domain, we do to this one exactly what we did with the last one. Bring down your radicand and make it greater than or equal to 0. You see, he can be a 0 in there, or a number greater than 0. X minus 1 must be greater than or equal to 0. Positive 1 on both. X must be greater than or equal to 1. Now, before I show that interval notation, let's just test this a bit. It's saying that x can be 1. If you put 1 in place of x, folks, 1 minus 1, 0. The radical of 0 is defined. It's defined. If you let x be greater than 1, you can let x be 2, 3, 4, 5, 6, 7, 8. Fraction, decimal, just as long as it's greater than or equal to 1, it will satisfy. Now, how do we take this x is greater than or equal to 1 and translate it into the interval? Well, because the equal sign is there, that means that the domain can be 1. Domain. You make a bracket. You put 1, comma, positive infinity, and you have the domain for that given 1. Now, I figured that was going to take a few minutes to go through and do that, and we'll just kind of stop at this point and catch our breath here a little bit, and then we'll move into the algebra functions. Thank you for right now. We'll talk later.